Venus is the ultimate spacecraft graveyard. The surface sits at a blistering 460 degrees Celsius, and the atmospheric pressure is 90 times greater than Earth. During the 1970s and 80s, the Soviet Union launched the Venera program, a monumental engineering effort to land on that surface. Even the most successful of these probes only survived for 23 to 127 minutes before failing. These probes were built like tanks, encased in heavy, pressure-resistant spherical modules designed to survive the deep ocean. But even with that level of robust engineering, the environment destroyed them almost immediately. Venera proved that surviving Venus is not a problem of armor or battery life. Instead, it is a fundamental challenge of physics. Almost every piece of modern technology relies on semiconductors, which use a microscopic wall called a band gap. This gap controls the flow of electrons, allowing microchips to sort them into the ones and zeros required for digital logic. At room temperature, this system works as intended. The barrier holds the line, carefully sorting the electrons and keeping the circuitry stable. But as temperatures approach the 460-degree mark found on the Venusian surface, a physical phenomenon called thermal carrier generation takes over. The extreme heat injects massive amounts of kinetic energy directly into the silicon. The electrons become so agitated that they simply jump the gap. The heat overwhelms the barrier, and the logic gates get stuck in a permanently open position. When that happens, the silicon effectively becomes a total conductor. A microchip's complex logic devolves into a chaotic slurry of electrical noise. At these temperatures, solar panels, electric motors, and digital radios become useless pieces of metal. To bypass this physical limit, a team of brilliant engineers are designing RE, the automation rover for extreme environments. NASA engineers are currently prototyping these designs at JPL, treating clockwork as a serious aerospace solution for the most hostile worlds in our solar system. The first major hurdle is power. Without solar panels, RE must rely on wind. The surface winds on Venus move at a sluggish 0.6 meters per second, but the atmosphere itself is incredibly thick, with a density of 65 kilograms per cubic meter. This chart compares Earth's thin, fast wind energy against the slow, thick atmosphere of Venus. It shows that they achieve equivalent power outputs because wind power is directly proportional to fluid density. A walking pace breeze on Venus carries the force of a high-speed gale on Earth. The rover captures this energy using an omnidirectional Savonius vertical axis turbine. Because it catches air from any angle, it can translate that immense rotational torque directly into a mechanical constant force spring. The same atmospheric density that crushed the hollow hulls of previous landers now acts as a reliable, infinite engine for a mechanical one. The second challenge is computation. Without a silicon microchip to act as a brain, engineers looked to the earliest mechanical computers of the 1930s for a path forward. Specifically, they looked at Konrad Zus's Z1 computer. Built before the transistor, the Z1 used precise mechanical qubits instead of electrical circuits to perform calculations. ARE adopts this exact concept, utilizing something called sliding plate logic. Instead of representing binary ones and zeros with electrical voltage, data is represented by the physical position of a sliding metal plate. Looking at this mechanical AND gate diagram, an actuator needs to move an output plate across a gap. If control plates A and B are on, they form a physical bridge, allowing the actuator to push the output forward. Otherwise, the output remains zero. By replacing microscopic electrical states with macro-scale mechanical states forged in heat-resistant alloys, ARE's brain becomes immune to thermal runaway. Solid metal plates will continue to crunch numbers regardless of the heat. That leaves the final challenge: communication. With digital radios melting, ARE needs to transmit data without generating any radio waves. The solution is a passive radar retroreflector, a corner cube mounted to the top of the rover. When an orbiting spacecraft sends a radar pulse through the clouds, this cube reflects that exact signal straight back into space. To turn that raw reflection into a message, the rover uses its wind-powered mechanical computer to pull a physical shutter back and forth over the reflector. It works exactly like the signal lamps used by naval ships, which rely on mechanical shutters to send messages across the ocean without modern radios. By systematically covering and uncovering the retroreflector, The rover is quite literally blinking digital data up to the orbiter via Morse code, solving planetary communication with zero electrical power. Past missions to Venus were suicide drops, fragile electronic probes collecting a few data points before melting in 30 minutes. ARI is designed for patience, built to sit on the surface and collect foundational data over months or years. This mission profile relies on an unexpected juxtaposition of technologies. We are sending an automaton powered by a windmill and calculating with World War II-era logic to transmit its findings to a highly advanced 21st century satellite orbiting high above the clouds. Engineering success on Venus relies on selecting materials suited to the environment rather than pursuing sheer complexity.